closed time-like curves and time travel are not a real physical possibility. There will be a recent thermodynamical argument due to Rovelli, which I think is not very convincing, and then possibly more convincing, but less definite mathematical results. So let me start with the introduction. We say that a point P chronologically presets Q if and only if there's a future directed time-like curve from P to Q, and this relation is always transitive. So if P chronologically presets Q and Q chronologically presets R, then P chronologically presets R. But in some spacetimes, this relation is irreflexive, so you cannot go along a future directed time-like curve from the point to itself. And in some other spacetimes, this could be reflexive. And when it is reflexive, then the spacetime contains closed time-like curves. And of course, closed time-like curves and alleged possibility of time travel raise deep questions, both philosophical, and there's a lot of both old and recent work on this, and physical. And again, there's a lot of interesting work being done here. A lot of this work concerns general features of CTCs, and in particular, Hawking's theorem aiming at establishing chronology protection conjecture concerns general features of CTCs. But today I want to look at particular exact solutions, especially in the context of the thermodynamical arguments against the possibility of closed time-like curves. So this is the picture that all of us know very well, the maximally extended Kerr spacetime, and I will focus on the sub-extremal case here. In this case, we have the globally hyperbolic 1 and 2 region. So the asymptotically flat exterior of the rotating black hole, the interior, and then an observer crossing to the interior could further cross the Cauchy horizon and enter the region 3 containing closed time-like curves. And this region 3 violates chronology, and although there are no closed time-like curves in the regions 1 and 2, there are closed time-like curves in the region 3. Another interesting feature of this spacetime is that it is what we philosophers call a Malam-Hogarth spacetime. So there's a point P and a future complete time-like curve gamma, which is fully contained in the chronological past of that point. And this is interesting because you may contemplate, for instance, locating classical computers on gamma and ask whether that could tell us something profound or at least interesting about limits of classical computability. And so the 3 topics of philosophical interest, determinism, because we have Cauchy horizon, time travel, because we have chronology violating region, and hypercomputation, because it's a Malam-Hogarth spacetime, happen to converge in a spacetime which has some astrophysical significance, in contrast with some of the other philosophically interesting spacetimes, which do not have astrophysical or indeed cosmological significance. And so this is potentially interesting situation. And I think it's natural to ask oneself, well, how likely it is that our universe contains chronology violating regions? Because Kerr black holes are, of course, widely used in astrophysics, and maximal extensions of the exterior Kerr metric contain chronology violating regions. So perhaps that's a possibility that should be seriously entertained. And I think it's good to sort of keep track of this possibility as physics develops, and this talk is partly in that direction. So, of course, there are many things you can say here. The first of them is that, well, hold on, it's only the exterior Kerr metric which is used in astrophysics. And even that has only been tested at some distance from the event horizon and up to certain precision. But the chronology violating region of Kerr is hidden well beyond the event horizon. in the interior of a black hole, and perhaps not all parts of the maximal extension should be interpreted as representing physical states of actual black holes. So the very fact that Kerr black holes are used in astrophysics doesn't on its own, of course, tell us much about whether our universe contains chronology violating regions or not. And well, unfortunately, in the foreseeable future, there are no prospects for having empirical access to the Kerr black hole interior. So currently only conceptual and mathematical methods can be used in addressing the question whether our universe is likely to contain chronology violating regions or not. And so again, that's a philosophically interesting situation. So before I get to some arguments which aim at establishing that Kerr black holes cannot operate as time machines, let me say something about what it may mean for a spacetime to be a time machine spacetime. And there's been some, I think, good and interesting philosophical conceptual cleaning up done on the issue of time machines. And so in this section, I will mostly advertise this work. So there seems to be a consensus that there are two general notions of a time machine. There's the Wellesian paradigm of a time machine and the Fornian notion of a time machine. So the Wellesian notion of a time machine is what you see in most, but not all, but most sci-fi novels or movies. You have an operator, you have some sort of a physical device, you dial the target date, past or future, throw a lever or push a button and sit back while time rewinds in this or that way, kind of like Back to the Future. And this is not a very philosophically very interesting notion. More interesting notion is a Fornian time machine, and it's because Kip Thorne and some of his collaborators were the first who kind of forcefully suggested the possibility that without violating the laws of general relativistic physics, some sort of advanced civilization might manipulate matter energy so as to produce closed time-like curves where none would have existed otherwise. And this way of thinking about time machines has been further developed by Smink, Earman, and Wüthrich. So the aim of their work is to clarify the sense in which operation of a time machine can be said to cause or produce closed time-like curves. And because closed time-like curves have associated with them various sorts of Cauchy horizons and chronological horizons, some of the straightforward proposals, for instance, that the specification of initial data or physical fields within a time machine region produces CTCs by a dynamical evolution, it's a no-go because the CTCs necessarily fall outside the region of spacetime fixed via dynamical evolution from the time machine region because the CTC region with the CTCs is always non-globally hyperbolic. So Smink, Earman, and Wüthrich propose another way of thinking about this, which is a sort of potency condition based on the intuition that although CTCs cannot lie within the region causally determined by the time machine region, they may be on the verge of forming in the sense that every possible extension of the time machine region contains CTCs. And then the issue of time machines basically reduces to existence of maximal extensions of spacetime satisfying various conditions, both local and global. To be more precise, the time machine satisfies at minimum the following conditions. There's a partial Cauchy surface, sigma, such that there are no closed time-like curves to the past of sigma. Moreover, the conditions that encode the instructions for the operation of the time machine can be set on sigma, and the region of spacetime containing the time machine belongs to the future domain of dependence of this partial Cauchy surface. time machine is confined to a finite region of space and operates for a finite amount of time. And the chronology violating region is contained in the causal feature of a time machine. And all of those conditions seem to be intuitively satisfied in case of gravitational collapse resulting in a Kerr black hole. There's one delicate issue that I'm going to kind of sidetrack. Feel free to ask me later. There's an issue of what sort of extensions of Kerr spacetime should be considered. Of course, there's a sort of natural extension with the closed time like Kerr's, but that whole region is not in the domain of dependence of the initial data in regions 1 and 2. And so we could produce all sorts of other extensions by cutting slices and splitting every closed time like curve into 2 and doing all sorts of tricks like that. And so we should, it seems, contemplate only hole-free extensions of the Kerr spacetime, but one may argue that there is no intuitively adequate notion of hole-free. And so then this raises some problems for a definition like that. But modulo these issues, it seems that if we are to take existence of region free of the maximal extension of the Kerr spacetime seriously, it seems that we have a candidate for a time machine in some precise sense. So that's, of course, philosophically interesting, but you may be bothered by this alleged possibility of closed time like curves and time travel. And so you may ask, well, are there some sort of other considerations, either physical or conceptual, which would or could limit the possibility of getting closed time like curves? And I will now discuss two groups of such arguments, starting with recent thermodynamical arguments due to Carlo Rovelli. So Rovelli's claim is that closed time-like curves are incompatible with the thermodynamical arrow of time. And the argument goes as follows. This argument will go through, I think, 3 next slides, and I'm not endorsing it, but it's a short argument, and I thought it's best to present it in the form of citations. Rovelli notes that, of course, traveling to distant future is possible in principle, travel fast enough, or spend little time sufficiently near to a black hole horizon. Can we travel to the past? And GR appears to suggest that it might be possible in principle because we have solutions with closed time-like curves, such as Kerr solution. But the idea of traveling to the past was always puzzling to people, and perhaps we can generate all sorts of paradoxes. And that's bothersome, but luckily, Rovelli will argue, paradoxes disappear if we examine with Kerr the full thermodynamical and statistical physics along the closed time-like curves. So that's the claim. And of course, naturally, if time travel to the past is thermodynamically impossible, then in particular, time machines are thermodynamically impossible. So let's see how the argument goes before we see how good it is. So the argument begins with the observation that any mechanical clock that counts oscillations dissipates energy. And so any clock is ultimately thermodynamical. For instance, a pendulum clock cannot work without friction. And if, as a good clock should do, it should count its oscillations, dissipation is needed, and so entropy grows. So take a measure of local entropy along the closed loop gamma, so that's one of the CTCs in our spacetime. For the clock to work all along gamma, registering the number of its oscillations, we need the entropy to grow with time everywhere around the loop. But since this is a loop, entropy cannot grow monotonically, and so it is impossible for a clock to count its own oscillations along a closed time-like curve. And if so, there is no physical way at all for a clock to count its oscillations. And this is more general than just clock counting, because if we would like to travel to the past and arrive to the past, keeping our memory of events which happened in the future, we would need some device like a brain, which is capable of memory, but the memory is supposed to be an irreversible phenomenon. And if we buy into the premise that all irreversible phenomena are based on the second principle of thermodynamics, then along a closed time-like loop, the only possibility of satisfying the second law of thermodynamics is that the entropy is constant, but if so, all the processes are reversible and there can be no memory. And so even though GR contains solutions with closed time-like curves, using those solutions for anything interesting runs into problems with thermodynamics. Okay, so that's the argument, how good it is.
Julius, may I ask a question?
Yes, of course.
There is, the very well-known argument, which actually is even better than the entropy increase, and that is, if you are on a closed time-like curve, you can get logical inconsistencies, like you can kill your parents, and that is a logical inconsistency. So why isn't that enough? Why do we need entropy?
Well, so there are few things to be said. One is that the logical arguments run into all sorts of difficulties, and one of the, I think as of now, sort of prevalent position among philosophers who worked on this is that most of the logical arguments actually do rely on linguistic equivocations. For instance, what does it mean for me to kill my own or to be able to kill my own grandparent, and things like that. And so I think many people find those logical arguments to be less than convincing. So that's one reason. The second is that, well, we seem to have mathematical solutions to the equations of physical theories, which do allow these sorts of possibilities. And so perhaps we should only contemplate certain classes of solutions, something like Novikov's self-consistent solutions. But saying that time travel is impossible for logical reasons would be a bit weird, because it would be very strong and it would rule out all sorts of interesting physical solutions on purely logical considerations. And I think many people are unwilling to do that. Shall I continue?
Yes, please go ahead.
So we have this thermodynamical argument, and I think on the face of it, it may look pretty convincing, but I hope to persuade you that upon closer look at the causal structure of some of the spacetimes with CTCs, it is much less convincing than it appears to be. So let me first consider the Gödel spacetime. The Gödel spacetime is actually the first GR spacetime containing closed time-like curves found in late 40s. So that's a rotating, non-expanding, geodesically complete exact solution of the Einstein's field equation with a dust source and a cosmological constant. Now, this spacetime is not a time machine in the precise sense I advocated for, because there are closed time-like curves going through any 2 points in spacetime whatsoever. And so we cannot think of this spacetime as a time machine where we have sort of piece of the universe which is safe for historian, and then the piece with the closed time-like curves. So it's not a time machine, but it's still interesting because I think it shows a certain flaw in the argument. And namely, it is well known that although there are closed time-like curves in Gödel spacetime, there are no closed time-like geodesics. And there's actually a series of results going back at least to work of Malamud in the 80s about the required minimum total integrated acceleration that you would need in order to enter one of the closed time-like curves. And so if you're in a space-time with this sort of causal structure, there could very well be physical ways for clocks to counter oscillations because you could simply place your clock on the geodesic, go traveling along the closed time-like curve, and at each point, you could ask yourself, okay, at which moment of time in the universe am I? By consulting the clock on a particular geodesic, sort of whenever I intersect with the geodesic again. So we could very well have clocks counting its oscillations in the appropriately monotonically in ways which are compatible with monotonically growing entropy in a spacetime with closed time-like curves. Second, the argument that we have seen so far assumed the particular form of the second law of thermodynamics.
Sorry.
And it's this one. Yes?
Would your interactions with the clock violate any of the thermodynamical restrictions on your own path in your closed time-like curve?
I think it's a good question. It's an open question. I don't have the answer. But actually, quite a few people started publishing papers on things like signaling between you and your past copies in Gödel spacetime. And so hopefully we will be able to have an answer for this. But thermodynamics of closed time-like curves hasn't really been investigated that well. So as of now, I think it's an open question.
Okay.
But a good one, yeah. Yeah, but what I think is a really serious problem with these sorts of arguments is that they assume the second law of thermodynamics in something like this form, and actually very explicitly throughout the paper. But the second law in this form applies only to isolated systems. And so should we or could we think of the chronology violating region 3 of Kerr spacetime as an isolated system? And I think not really. First of all, the matter can flow in from the exterior through the Cauchy horizon. And if we consider as a serious possibility existence of other copies of the regions 1 and 2, then entropy could also leave the region 3. And this is even before we start thinking about thermodynamical nature of it can flow in from the exterior, then this means we're dealing with an open system. So the right equation should be some sort of unspecified balance equation rather than this simple equation here. And the choice of the appropriate terms in the balance equation seems to be rather tricky and seems to depend on our prior decision of regions which are physically significant. For instance, whether we consider those additional copies of regions 1 or 2 significant or not. And so for this reason, I think we should consider the Rovelli's arguments based on the second law of thermodynamics as less than convincing. How much more time do I have, Paul?
Let's say 10 more minutes.
10 more minutes. Okay, great. So in this last part of the talk, what I would like to do is, so far, I went through an argument that I have found not very convincing, and I will now summarize some arguments which may be more convincing than thermodynamical ones. So, of course, if there are no Cauchy horizons, then there are no time machines. And in particular, a version of the strong cosmic censorship hypothesis states that for generic initial data sets, their maximal globally hyperbolic developments are inextendable. In case of Kerr, this implies that there is no region free, and if there is no region free, then there are no CTCs. And so perhaps then kind of GR could deal with the alleged possibilities of CTCs on its own, or perhaps with a little help from QFT and Kerr spacetime, and there would be no need to involve statistical mechanical arguments at all. If it would be the case that for generic initial data sets representing, say, something like perturbations of the Kerr spacetime, we get no region free, then the possibility of CTCs would be a highly fine-tuned one. And so perhaps there would be no stably operating type machines, which would be, I guess, the second good thing. There are quite some indications that cosmic censorship is true for Kerr black holes. So let me first discuss very briefly a close related cousin, the Reisner-Nordström black holes with the de Sitter boundary conditions. So there are arguments in the literature that cosmological blue shift due to de Sitter boundary conditions may prefer current vector blow up for near extremal Reisner-Nordström black holes. But it has been argued that contrary to the Reisner-Nordström case, in the Kerr case, decay of the quasi-normal modes is such that the cosmic censorship is respected. And it has been argued that in the Reisner-Nordström case, the possibility of extension to the horizon is an artifact of the choice of not large enough class of initial data sets. And so if those results are on the right track, then they give some support for the cosmic censorship conjecture, and therefore support for the view that Kerr black holes are not viable time machines. And there are also numerical results by Paul Chesler, Eric Collier, and Ramesh Narayan, which I think can be interpreted as a suggestion that for delay times, the singularity structure of rotating black holes becomes space-like. And so again, the rotating black holes would likely not be viable time machines, except for the highly fine-tuned cases of initial data. So those are two groups of classical results. And there are also at least two types of semi-classical results, which seem to constrain possibility of extending black hole spacetimes through Cauchy horizons. First, there's a version of cosmic censorship following from the behavior of the stress energy tensor in QFT and Kerr spacetime in recent work by Hollands and Wald. So the claim in that work is that for the Reisner-Nordström de Sitter black hole, the expectation value of the renormalized stress energy tensor blows up at the Cauchy horizon, and it's also expected to blow up in Kerr de Sitter as well. And so even if there would be a possibility of extending the spacetime to region free from the point of view of classical GR in something like Kerr de Sitter, then inclusion of additional physical effects would prevent that possibility. And there's also a sort of generalization of the Hawking 90 true result on chronology protection conjecture, which gets rid of the energy condition and uses generalized second law of thermodynamics in its place. But this generalized second law of thermodynamics is very different from the thermodynamical arguments due to Rovelli, because the generalized second law of thermodynamics is only concerned with the growth of the area of the event horizon and entropy in the exterior, and doesn't tell us anything at all about what happens in the interior. So to conclude, I think there may be good reasons for denying that closed time-like curves could be a feature of our universe, and I think those classical and semi-classical arguments could be some sort of, perhaps not as of yet definite, but a form of support for disbelieving that closed time-like curves could or are a feature of our universe. But the arguments from standard thermodynamics do not seem to be such good reasons. And yeah, I think that's all. I just have a few more slides with the references if anyone is interested. Thank you.
Everybody's clapping. Just can't hear it. So questions for Julius, guys? Just
Julius, obviously the Kerr solution is not complete because it doesn't have quantum mechanics near the singularity. And so the question is, do you expect, even if classically the CTC implied by some calculations, that quantum mechanically it will be avoided?
Mm-hmm. I think the I think the results by Hollands, Wald, and Zahn from last year are a sort of hint in that direction. Yes, yeah. Well, they're hints in that direction in the sense that they talk about quantum effects at the Cauchy horizon, not near the singularity. Arguably, we would need a full view of quantum gravity to tell us what happens near the singularity. And I think the expectation of people working in quantum gravity is that the singularity will be resolved, space-time could be extended, and that all of that should happen in the nice deterministic way without any causal weirdness such as CTCs going on. But I think one could very well question whether the expectation that the extensions, that those quantum extensions of space-time will be closed from 3TCs is a good position to take, because many frameworks people are working with, such as loop quantum gravity, assume a 3+1 decomposition of space-time from the start. And so one could say, well, that's not a justified assumption in the context of something like Kerr singularity. So I personally wouldn't bet either way.
there's also a classical argument, which you've more or less said here, or alluded to at the very least, which is that this region 3 is not unique. You can certainly study Kerr in that region and ask, are there closed time-like curves in Kerr? But you could have chosen, infinitely many different geometries in region 3, which are not Kerr metric, which would not have closed time-like curves.
Yeah, and I think actually one could claim that most of the extensions we could contemplate will have no closed time-like curves. By a simple Kantian argument, take any extension with closed time-like curves, and it's trivially easy to produce uncountably many different extensions from that one by removing closed subsets and appropriately using appropriate conformal transformations or whatever other tricks like this. And so for any extension of a spacetime with CTCs, there will be a whole bunch of extensions which are CTC free. The sort of way that one could hope to deal with all those other extensions is to say, well, for all sorts of other reasons, we should demand that spacetimes are hole-free in various ways, because once you start to allow these sorts of tricks, then you can also modulate globally hyperbolic developments, and we wouldn't like to do that. And perhaps then this notion of hole-freeness would also be kind of sufficiently strong to rule out all those unwelcome extensions of Kerr, which do not have closed time like Kerr's. But there is no like single such notion of hole-free spacetime, and actually, in a way, all these notions are not very good. And so if one takes this into account seriously, then perhaps there's another good reason for, for not believing that Kerr is a time machine, indeed.
Very good. More questions, guys?
If there are no questions, I wanted to say a few words afterwards, Paul.
Okay, go ahead, Avi.
Okay, so thank you very much, Julius. That was a very illuminating, very interesting talk, and you were the first in our series over Zoom to have a BHI colloquium over Zoom, which is a new experience, I should say, but it's less challenging than giving a class. After giving a class yesterday, I must say that getting participation in a class is very difficult with Zoom. Basically, everyone keeps silent, people do not respond. But we enjoyed very much your colloquium. It's appropriate for this kind of a format. And it was recorded. So in the coming weeks, we will hold the same with other talks by other speakers. And we encourage anyone within the BHI to contact Paul Chesler or Fabio Pacucci if they're interested in speaking, because we are missing some slots of people that decided to postpone their visit rather than speak through Zoom. A general point I wanted to make is that since we aren't able to meet each other in the corridor and discuss things, feel free to organize your own Zoom meetings. Harvard provides that for free, and using the same operation as the BHI colloquium, you can establish a conversation with anyone you want. In fact, at the ITC, one of the postdocs established a meeting, a permanent meeting at the cooler. So anyone that would like to sort of join can join at any time during the day. And if there is someone else there, they can chat and so forth. And I encourage you to have the same substitute for our corridor over Zoom. We all hope, I mean, I'm participating in these Zoom meetings with the deans on a regular basis, and there is the hope that, perhaps within the coming month or two, things will get better, but it's not at all clear at the moment. There is a lot of uncertainty, and really the fundamental uncertainty, if you follow the news, is whether the US will go in the path of Italy or whether it will go in the path of China. And it's not at all clear because if you open the news right now, you will see that there is a strong pressure from the business community on the White House to allow people out so that the economy will not collapse. And if that happens quickly, if that happens within a week, when the virus is still around, it may bring us to the same path as Italy is going through, with hospitals being flooded with people that they are unable to treat, and then with a situation that is far worse for the economy. So trying to save the economy by letting people out will actually hurt the economy. And so it's not at all clear whether the situation, if people go out, whether things will go bad for even a longer time after that. Yes.
Do you think that there are other paths in Italy and China? For instance, South Korea just had a highest number of tests per capita, or among the highest, and they tested like 300,000 people, and they also had good outcomes. And it could be that there are just different, specific issues with different populations. Like Italy has among the highest median age in the world among countries, and it could be that there are other like maybe doing what South Korea would be like a third path, for instance. And
well, this is a very good question. So to clarify again, it's not just South Korea, also Singapore avoided a catastrophe. And the reason they did that, they succeeded, is timing. It's more timing and testing. So basically they identified the risk very early because they had the SARS threat a decade ago. So they already went through that psychological threat. And so they had the machinery built in to operate on a short time scale. And so they immediately started testing in a very massive scale, especially in South Korea, over 100,000 tests, when the US was executing maybe 1,000 or so at the beginning and very slow to respond. Timing is extremely important when you deal with exponentials. So just to give you an example, 1 day of delay in the way that China operated would have saved, 60% of the people that died over there. So it's really about timing. And South Korea acted very promptly, and they were able to succeed. The US, on the other hand, Italy obviously did not do anything. And, the mayor of Milan was encouraging people to go out. And as a result, once you recognize the problem is there, it's too late. The analogy of a pond, where let's imagine lilies, on the surface of the pond, and let's imagine a doubling time of 1 day, and overall 60 days for the lilies to cover the pond, which is roughly the time it takes for this virus to basically infect everyone. So imagine that every day you double the area of lilies on the pond. So guess what? When is the pond cover halfway? It's 1 day before the 60th day. So once you recognize that the pond has all these lilies on it, because previously it was very few of them, far and apart, once you recognize it, you're already at the end of the process, and then, it's very difficult to prevent it. So that's the problem with viruses, that this exponential growth allows you to see the impact when it's too late. And you have to be smart enough to act early. And that's what South Korea did. And aside from that, there is one interesting example that I should note that is not understood at all. And that is in the category of what you described, and that is Japan. Because Japan seems not to report about a lot of cases, and nevertheless, they didn't do much. And one possible explanation is that they want the Olympics to take place there, and so they are keeping all the sick people at home. But I'm not sure that that's the case, and it may be genetic. It may be something, maybe the population there is not responding the same way as the rest, of the rest of the world to this virus. But Japan is an outlier in that regard. South Korea is a very fast-moving actor, and the US is 1 week behind Italy, basically. And it's quite possible that it's too late now for the US, but we shall see. And if, the main worry is really the economy that could collapse. It's already downhill, but it could go very far down. And we all have to monitor the situation, because that will impact universities, through the endowments that they have. So Harvard may lose a lot of money through the endowment, but also it will impact them, other activity. We will have to continue with this Zoom for a while, and that suppresses the productivity in some sense of people that interact with each other. For me, it's not a big deal personally, because I executed social distancing long before it was trendy. I prefer to sort of not to socialize, but there are many activities that we do, and many types of science where interaction is extremely important. And And also the economic challenge will suppress innovation, because when the resources are limited, people tend to be very conservative. And so that's a worry. I was just before this colloquium, I attended the meeting of the National Academies of Sciences, where there was a discussion about the plans and how things will influence the bigger picture. And it was just this point that there is a lot of concern about how next year would look like for the academic world and the research world. We just have to monitor the situation and hope for the best. The good news is that, you know, we have everything waiting for us once things ease up. And the bad news as of an hour ago is that the president of Harvard University, Larry Bacow, and his wife, Adele, both had the symptoms of COVID-19 on Sunday, and they got tested and they were found positive an hour ago. So, I mean, suddenly the people at the top are most vulnerable because they meet a lot of people and they touch a lot of surfaces. And that illustrates why it's so important for us to stay at home so that we don't risk getting infected. So I wish everyone good health. And by the way, the statistics in Massachusetts is that about half of the patients are below age 50 and half above. It's not at all clear that locally it's very age sensitive, at least according to the number of people that go to the hospital. And so I encourage everyone to be careful. And I look forward to seeing all of you in a week.
Thanks again, Julius.
Yeah, thanks.
Thank you, Julius.
Thank you, everyone.
All right, everyone, take care.
Yeah, bye-bye.
Yeah, okay, bye-bye.